You ever wonder what makes your coffee maker smart? Or how your car's dashboard can just instantly react to things? Well, today we're diving into the tiny, pretty much invisible brains that power our world, and the really clever trick they use to handle everything at once.
So here's the plan. We're going to start with the hidden world of these little computers, these microcontrollers. Then we'll meet the rock star of the chip world, the PIC. We'll find out about a huge challenge they all face, and then the elegant solution that makes our modern lives possible. And we'll even peek at some real code to see exactly how it's done.
Just think about your morning. The alarm clock that wakes you up, the microwave that heats your breakfast, the car that gets you to work. I mean, every single one of those things has a tiny, dedicated computer working silently behind the scenes. We're literally surrounded by them, but we never even see them. Now, unlike the big, powerful processor in your laptop that's juggling, a dozen different programs at once, a microcontroller has one job, and only one job. Its entire existence might just be to read a temperature sensor or to control a little motor. And that laser-like focus is what makes our devices so incredibly responsive and reliable. Okay, so if these tiny brains are everywhere, what are they? Let's zoom in on one of the most popular and influential families of microcontrollers ever made, the PIC, from a company called Microchip Technology. The story of the PIC is a classic underdog tale. It actually started out back in the 70s as this humble little support chip. Its job was just to help bigger processors with simple tasks. But here's the thing. It was so good at its job that engineers realized it could do so much more. Its design, this Harvard architecture, just means it has separate, super fast lanes for instructions and for data. That made it quick and simple. It became a star in its own right, and, well, the rest is history. So why did the PIC become such a superstar? Honestly, it was the perfect storm. It was cheap enough for students to use in their first robot projects, but it was also powerful enough for engineers to build complex factory control systems. Its architecture, called RISC, basically means it does more with less, running these simple, lightning-fast commands. It was the people's chip. It really did change the game. And the PIC family is kind of like a fantastic toolbox. You've got your small, simple screwdrivers for the basic jobs, right? But you've also got powerful drills for the heavy-duty tasks. The 8-bit PICs, those are your screwdrivers, perfect for simple things. But the 16 and 32-bit versions, those are your power drills, capable of handling really complex math for things like audio effects or super precise motor control. So we've got these powerful little brains, but they face a really fundamental challenge. Picture a washing machine. The microcontroller is busy running the wash cycle. It's spinning the drum, controlling the water. But what happens when you press the pause button? How does it even notice you did that while it's in the middle of a totally different task? Well, the dumb way to solve this problem is called polling. It's like having a kid in the back of the car on a long trip, just constantly asking, "Are we there yet? Are we there yet? Are we there yet?" It's incredibly annoying, and it wastes a ton of energy. The processor is so busy checking for that button press that it can barely do its actual job. So polling is a terrible solution. It's inefficient, and it makes our devices feel slow and unresponsive. There has to be a better way, right? How can a device be both efficient with its power and be instantly responsive? And of course, there is a better way. It's this elegant and really powerful solution called an interrupt. And honestly, the best way to understand it is to think of it like a doorbell for your processor. See, instead of constantly checking the front door, the processor just gets on with its work, completely focused on its main task. But when someone presses a button, ding dong, the doorbell rings. That's the interrupt. It's a signal that says, hey, something important just happened. You need to deal with this right now. So what happens when that doorbell rings? The processor doesn't just drop what it's doing. It carefully puts a bookmark in its work so it can come right back to it later. Then it goes to answer the door. That special code for answering the door is called the Interrupt Service Routine, or ISR. Once it's dealt with the visitor, it goes back to its bookmark and picks up its original work exactly where it left off, as if nothing ever happened. Okay, so how does the processor know which doorbell to answer and when? It uses a set of software switches. There's a flag that pops up when a doorbell is rung. There's an enable switch that lets you, the programmer, decide which doorbells you even want to listen to. And then there's a global master switch that turns the whole system on or off. Well, okay, now this might look like a complicated mess of lines, but what you're seeing here is the genius of the chip's design. This is the physical hardware, built right into the silicon to manage all the different doorbells. It's like having a super smart butler who can prioritize who to let in first. A fire alarm is probably more important than the pizza delivery guy, right? Well, this circuit is how the chip makes those decisions in a fraction of a second. Theory is great, but let's actually see how this works in the real world. We're going to look at a classic example, making an LED blink. But instead of an external button press, we're going to use an internal timer to ring the doorbell at a perfectly regular interval.
So before you can use an interrupt, you have to tell the chip what you want it to do. It's really just like a pre-flight checklist for a pilot. You set up your timer, you make sure its doorbell flag is down, you tell the chip which specific doorbell you're listening for, and then you flip the master switch to say, okay, I'm ready for takeoff.
So the doorbell rings, and the processor immediately jumps to that special ISR code. And the very first thing it does is look through the peephole to see who's there. Was it the timer? Was it a button press? This line of code is how it checks the flag to see exactly which event actually happened. And here's the beautiful part. Once it knows who's at the door, it just takes care of business. In this case, it's just one simple, elegant line of code that flips the LED. If it was on, it turns off. If it was off, it turns on. It's incredibly efficient. Now, this is maybe the most important step of all. After you've answered the door, you have to tell the butler that you're done. You must manually reset the flag. If you forget to do this, that doorbell will just keep ringing, and the processor will get stuck answering the same old news, unable to do anything else. And that's the secret. This isn't just for microcontrollers. It's the foundation of all modern computing. It's the reason our devices can feel so smart and so responsive, while being incredibly power efficient. They let the processor sleep when it's not needed and wake up in an instant when something important happens. It's truly the best of both worlds. And get this, the scale is just mind-boggling. By 2013, Microchip was shipping over 1 billion of these tiny brains every single year. 1 billion. That's 1 billion more devices in our world, all using this elegant concept of interrupts to make our lives a little bit smarter and a little more efficient. So the next time your phone buzzes with a notification or your microwave beeps when it's done, just take a second to think about the invisible dance that's happening inside. It's a world of interrupts, constantly managing the conversation between our physical world and the digital one, all happening in the blink of an eye. Makes you wonder, what other invisible systems are running our world right under our noses?